Okay, so this is the Tarzan problem from the physics final. So I'm just going to go through what he gave us in classroom, and on the final they're going to give you something different, like different givens, but should be the same idea, so this should hopefully help you out. So the givens here are the force of the water, which is N, Tarzan's mass, which is M, the length of the rope, the height above the water, and the angle of the rope. Okay, so in the first part of the problem, you're trying to find the velocity at the end of the rope swing. So in order to do that, first we need to find the change in height. So in order to do that, we know that the length of the rope is L, and it's going to go down a little bit. So you do some trig to find this thing, and then height's just going to be, let's say that's X. Height's just going to be the total length minus that X. So you could just do SOHCAHTOA. Cosine theta equals x over the hypotenuse, which is L. So x equals L cosine theta. So the height is L minus L cosine theta. Alright, so now we're going to use some energy because this is circular motion and that's weird, so we don't want to deal with that. So I'm not going to put anything in the O because I don't care. So we're going to have it start off as all energy from gravitational, and then at the end it's just going to be all kinetic energy. Alright, so say that the gravitational is the kinetic, so mgh to g 1/2 mv squared. So then you could find this, which is the final velocity. So velocity, okay, so the masses cancel out, equals square root of 2gh. Alright, so now you know the final velocity is square root of 2 times the gravity, which is 9.8 newtons per kilogram, times the height, which we found over here, which is L minus L cosine theta. Alright, so there you go. That's Tarzan's final velocity when he's letting go of the rope. Okay, for this next part, we need to find the velocity when he hits the water. So for this, we're going to just use some of the constant acceleration equations. So we know his horizontal velocity, but his vertical velocity is 0 because he's going horizontal. So you can write that his initial velocity is 0 meters per second, because we're just working with the y here. So now the acceleration is from gravity, so it's 9.8 meters per second squared, and down we're saying is positive, so that's a positive. And then the change in y we found in the last problem, that's the height of the cliff minus that little bit that he goes down in the rope, so that's minus L minus cosine of theta. Okay, so now that you know all of these, you need to find VF. So you use the equation VF y squared equals initial velocity y squared plus 2a triangle y. Alright, that's just one of the equations. So now that's equal to square root of initial velocity, that's 0, plus 2 times the 9.8 meters per second squared times the change in y, which is L minus h plus L cosine theta. Alright, so you plug that in and then you're good. But that's the final velocity just with the y. What we want is the actual final velocity. Now we knew what the x velocity was from the last problem because that was what we found, his speed coming off the rope. And there's no acceleration horizontally, so that stays the same. So if you draw a little triangle here, you know that's the x1, that's the same as in part A, and then that's the y. Now, that's theta. No, never mind, I already used theta earlier. Used squiggly line. And then that's the actual final velocity. So in order to find that, you know these two, so you just do Pythagorean theorem. So the final velocity is just square root of the x1 plus the y1. Alright, so then you calculate that, and then there you go. That's the end of part B. Okay, so in this part we're just trying to find the angle that it goes into the water, and we already know what the velocity x, y, and just the normal final one are all from earlier parts. So we could just use any trig function to find that out. So we could just use the tangent, the squiggly line is VFY over VF x. Wait, yeah, I'm stupid. Alright, there you go. And then you just plug it in your calculator, and then you know the angle. That part's pretty easy. Also, side note, in that last part, part B, you could have used energy methods for it, but I just like the 2D motion ones better. I don't know, whatever puts a turtle in your girdle. Okay, so now we need to find out how far through the water he goes. And in the last problem, we found the speed he gets into the water. So we're going to need to know that the force that the water exerts against him is F. So we know just from physics that the net force is mass times acceleration, and the only force acting in this case is just the F. Well, the F is acting against him, so it should be negative F equals ma. So the acceleration should be negative F over m. So we're gonna use the constant acceleration equations again. So we know the initial velocity from the other parts, and yeah, let's write v naught. And then we know the final velocity is going to be 0 because we're trying to find out when he stops. So we want to find triangle x in the equation vf squared equals v naught squared plus 2a triangle x. So triangle x is the final squared minus the initial squared over 2a. Oh, 2a. Alright, so the final is 0, so it's just negative initial squared over 2 times negative f over m, and then the negatives cancel out because you can't have negative change in x, it doesn't make sense. So times m over 2f. Alright, there you go. That's the distance he goes in the water. But that's an angle when it's asking how far below the water does he go. So that's the next part. For the final part, you need to find how far below the water he goes. So you know the angle he gets in the water, and you know how far he goes. So this is just SOHCAHTOA. So sine of the angle is change in y over d. So change in y is just the distance times sine of that angle. And you found both of these things in earlier parts. And that's the final answer. Also, this is just a random thing. It's kind of useless, but if you plugged in all the original values for the stuff, like the distance and the sine of the angle, that up here, that's what it would be in terms of all the original stuff. But when you're doing the real problem, you're going to want to like approximate after each part. So just do each step one step at a time. And he's probably going to make it backwards, make something dumb like that, but if you just do this kind of thing, it should be pretty easy. Alright, good luck, kids.